people had to. All right. So, we're ready to talk geometric sequences. What made an arithmetic sequence an arithmetic sequence? Are you okay? We added the same number every time. Well, this is an example of a geometric. What pattern is happening? Yeah, that's my multiplying by 4 every time. So yes, geometric sequences multiply by the same value each time. So would it be geometric if it multiplied by 1, then multiplied by 2, then multiplied by 3, then multiplied by 4? That's not the same value. So the key thing is it has to be multiplying by the same number every time. Well, is this one geometric?
Wait, what's the first one?
81, 54.
Yeah, I think if you're multiplying by a fraction, but I don't know what that fraction is.
Exactly. You can multiply by fractions, so therefore the numbers can get smaller. It's still geometric. So we need a way, how do I figure out what I'm multiplying by? By the way, the number you're multiplying by is called the common ratio. Last time it was the common difference. Now it's the common ratio. And that would be R, yes. Okay, so we need a way, like on the first one, how could you mathematically have figured out that R was 4? There you go, the second number divided by the first number. So that's the way you can always find the ratio. If it's not something that's obvious, you can do the second number divided by the first number, and it'll always get you the ratio. So if you're not sure what it is on this one, do second divided by first and reduce it. Okay, how did she get 2/3? If you pull out 9, you go down to 6/9, which divided by 3 takes you down to 2/3. Also, if you haven't realized it, if you just type 54 divided by 81 in your calculator, it will, and hit enter, it will reduce the fraction.
Actually, I guess 24 divided by 36, because those are smaller, easier numbers.
Okay. So you can't get that other. Okay, now, here's another interesting case. Is this geometric? If it goes 5, negative 15, positive 45, negative 135. Is he right? He's multiplying by negative 3. So, is it okay for it to go positive, negative, positive, negative? Yeah, if your ratio is a negative number, it's going to do that. Perfectly fine. So if you see it alternating, don't flip out about it. That just means it's a negative ratio. Okay, well, we essentially want to do the exact same kind of problems you just did. I want to be able to find a certain term down the road, the 10th term, the 50th term, whatever. I want to be able to sum up the terms. So I don't think you want to list these out by hand, because if you think about it, these are going to get to be big numbers really fast. Or icky, horrible little fractions really fast. So instead, we need a formula. So we're going to take a nice simple example here and see if we can come up with a formula. Okay. In this case, what's the ratio? 3. No big deal. Okay. What I want you to do is, there's a pattern here if you start looking. We could say 6 is 2 times 3. First number times the ratio. Couldn't I say 18 is 2 times 9? 54 is 2 times 27. What do 3, 9, 27? They're powers of 3, aren't? Yeah, that's 3 to the first. 9 is 3 to the second. 27 is 3 to the third. So if we translate that pattern into a formula, we've got our formula. What was 2, the first term? I just told you, sorry. Yeah, and sorry, I don't want a fraction yet. That's the next term. This is how to find a certain term in a geometric sequence. Why is 3 the base number every time? because 3 is the ratio. Yep, the common ratio. Now here's the tricky part. How do I figure out what power to use?
Number minus 1.
Yeah, because this was the first term. This is the second term. I used a first power. When I was on the third term, my power was 2. When I'm on the fourth term, the power is 3. There you go, it's n minus 1. So you are going to do lots of exponents when you plug these in your calculator.
So that's one of the
That is, yes, one of the formulas. And once again, you don't have to memorize these. I will give these to you. That's not what we're up to yet.
Is that n minus 1?
That is an n minus 1, yes. Infinity? Well, we are going to get to infinite ones. We're going to sum up infinite ones here at the end, but we're not there yet. All right, so suppose I gave you this particular sequence. 150, negative 60, positive 24, dot, 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 dot. And I said, find me the 7th term. So I want the 7th term. So I got to fill in this formula. First term is what? 150. Okay, we got to figure out the ratio, which is not totally obvious here. Yeah. Second divided by first, you can cancel the zeros. So 6/15 would reduce to 2/5. Okay. 2/5 is exactly 0.4. If you get fractions that are exact decimals, you may use the decimals. But like that one that was 2/3, you can't change that to put in like 0.66 or something. It will mess up your answer. So you need to carry the fractions if they're not exact decimals. In this case, we could do 0.4 and it would be okay. Got a preference? I drew a big parenthesis. You can type in 0.4 or 2/5. Now, here's the question. What's the n minus 1? How many terms are you doing? We're doing 7 terms, so therefore it's 7 minus 1 or 6 power. And once again, you definitely want to punch all that in your calculator at once. Don't do it in little pieces and parts, because those fractions are going to be nasty. Just throw the whole thing in your calculator at the same time. Now, I just changed this, so let me see if I can come up with the answer. If I divided that by 3. No, wrong. Whoa, I'd have to multiply it by 5/2. Is it 3? Somebody want to try? Is it 384 over 625?
Yep.
So that's the 7th term. As you can see, ugly 7th term. Would not be fun to calculate these by hand. Because you can get some nasty fractions pretty quick. Okay, so let's look at a real-world example of where one might use this. Can I switch? How am I doing time-wise? Oh, we're good. All right. We're going to the town of Zeno. That's what they said this morning. Unfortunately, Zeno's population is decreasing by 8% per year. That's a lot. Okay. The current population is 2,100 people. What will it be in 7 years? Now, we have to get rid of a fallacy on this one.
What year is it?
Now, those could be Seneca a few years back, where I think it's under 2,000 now, but it used to be in the low 2000s. But Seneca's not dropping at 8% a year. So my question to you is, it's 2,100 right now. How many are there next year? Just 1 year away. How do you figure out how many there would be?
Multiply it by 0.08 and subtract.
Okay, you're saying if I take it times 0.08, 8%, next year's population is 168 people?
No, you have to subtract.
Okay, but I don't want to do it by subtraction. I want to do it by multiplying by a certain number.
Well, you're decreasing.
I am decreasing. It's the same thing we learned to do with those log formulas. If you want to decrease by 8%, you have to start from what percentage? 108. You want to go up 8%? There we go. You have to take off the 8%. You're going to keep 92% of your population. You're losing 8% of it, but you're keeping 92% of it. So to figure out what your next population will be, you need to multiply it by 92%, not 8%. So that would put us down to 1,932. That's a lot of people, yeah. Okay, so I want to know what it's going to be 7 years from now. My question is, am I finding the seventh term?
So you're finding what the population is.
On average, like.
Well, because I'm going to just keep multiplying by 92% every time. So it's going to be geometric. I'm going to put it in in a formula, but my question is, am I finding the seventh term, the eighth term, the sixth term? Which term is it I need to find here?
When was the town founded?
Okay, right now, 2100 is the first term. It wants to know after 7 more years. So if I'm already on 1 and I go 7 more,
1 plus 7.
it's going to be the 8th term I need to find, not the 7th. This is 2100 is where we're working from. I mean, you could go back by any. Okay, so, what's first term? 2,100 times a ratio of 92% that we're keeping, and my power would be 8 minus 1, or the 7th power. And this is pretty shocking. So after 7 more years, they're down to 1,171 people.
That's a lot of people.
That's a lot of people to lose in a few years.
A bunch of people.
Maybe lost a lot of businesses or something.
People die.
But they had a nuclear leak or something that killed off lots of people? Build a highway to bypass the town and nobody comes to town anymore. Like cars, there we go, yeah.
I just watched that.
It could be Radiator Springs all over again. Okay, I didn't mean to inspire you to music, but...
Music.
All right. So, that's finding terms in a geometric series.
Not a good place to stop.
Yes.
2,100 commas. But it would be cars.
1,932 would be the second term.
Oh, okay.
I was just listing what the population was doing. Okay, so now let's sum them up.
Summonizing.
If I take all those terms and I want to add them all together, think how big some of these sums could get. Yes, these can be really big numbers, or they can be really teeny tiny fractions. If you add up a whole bunch of fractions, this can be a really fraction answer. So, warning, these will not necessarily be beautiful solutions.
You're almost at 15.
Oh, thanks. Good place to stop then.
That's why